The acronym RAID stands for Redundant Array of Independent Disks, though it is argued by some sources to stand for Redundant Array of Inexpensive Disks. Regardless of the exact phrase to which one subscribes to, RAID provides a means of both fault tolerance and performance enhancement in computer information systems. First, let's take a look at RAID Level 0. RAID 0 implements block-level striping without parity or mirroring. In this way, it provides increased performance during read and write processes, but it does not provide any fault tolerance. If any disk fails in the array, all data is lost. Increasing the number of disks in the array increases performance, since data can be broken into pieces and written to and read from multiple disks in parallel fashion. However, this also increases the chance of failure and the risk of data loss. Once again, the performance enhancement that comes with striping occurs because data can be broken into chunks and written to and read from multiple physical disks simultaneously, thus increasing the sum aggregate total amount of available bandwidth in the read and write input and output processes. For example, 96 kilobytes of data, if split into 3 32 kilobyte chunks, could be written to 3 stripe drives connected to 3 separate controllers simultaneously much faster than writing the entire 96 kilobytes of data to only one single drive connected to one single controller without any striping. After RAID 0 comes RAID 1. RAID 1 is mirroring without parity or striping. One physical disk completely mirrors another. As such, mirroring provides fault tolerance without a significant performance boost. If one physical drive fails, the other has a complete copy of its data and can keep the array running until a replacement drive is added and the mirrored set is rebuilt. Next is RAID 2. RAID 2 provides bit-level striping with dedicated parity, using binary or linear Hamming code and synchronized disk spindle rotation with each sequential bit stored on a different disk, providing a significant performance enhancement for read and write operations. At least one disk is dedicated to parity, providing for fault tolerance. Next is RAID 3. RAID 3 provides byte-level striping with dedicated parity and synchronized disk bundle rotation with each sequential byte on a different disk, providing a significant performance enhancement for read-write operations. Again, at least one disk is dedicated to parity, providing fault tolerance. Next is RAID Level 4. RAID 4 provides block-level striping with dedicated parity where parity data is stored in a single physical disk. It provides some performance enhancement due to parallel input-output operations, and provides fault tolerance through parity. Since parity is confined to a single disk, performance is not as great as with RAID 5. Next in line is RAID Level 5. RAID 5 is block-level striping with distributed parity where parity data is stored on multiple physical disks. This provides greater performance enhancement than RAID 4 due to parallel input-output operations on both data and parity disks, and provides fault tolerance through that same parity. A RAID 5 configuration is fault tolerant with any single drive failure, and the array remains up and running and therefore able to reconstruct data from remaining sets of both striped data and parity blocks. However, if more than one drive fails at the same time, the entire disk array goes down. In other words, if one of the data stripe drives fails, it can be rebuilt with the drive holding parity information, and if the parity drive fails, you still have the data stripe drives. Finally, we have RAID Level 6. RAID 6 provides block-level striping with double distributed parity, where parity data is stored on multiple physical disks. This provides a greater performance enhancement than RAID 4 due to parallel input-output operations on both data and parity disks, and provides greater fault tolerance than RAID 5 through that same parity. A RAID 6 configuration is fault tolerant with any 2 simultaneous drive failures, and the array remains up and running and able to reconstruct data from remaining sets of both striped data and parity blocks. However, if more than 2 drives fail at the same time, the entire disk array goes down. Modern Windows operating systems support software RAID. Windows 7 supports RAID 0 and RAID 1 configurations, and Windows 2008 server products support RAID 0, RAID 1, and RAID 5 configurations. Windows also supports 2 partition styles, Master Boot Record or MBR, and Globally Unique Identifier Partition Table or GPT. First, let's take a look at the MBR or Master Boot Record partition style. Partition capabilities include 2 possibilities: up to 4 primary partitions, or up to 3 primary partitions and 1 extended partition that can contain a maximum number of 26 possible logical DOS drives under old FAT and MS-DOS formatting, and an unlimited number of logical drives using modern mount points and file systems. It is recommended that Windows be installed on a primary partition, although many operating systems like Linux work quite nicely on extended partitions and logical drives, such as with multi-boot configurations. The maximum volume size of the NBR partition style is 2 terabytes. It utilizes hidden sectors to store system information, and it does not provide replication or CRC. Although Windows will work just fine with the GPT partition style, the NBR partition style is the default with Windows and the most compatible in multi-boot configurations. That being said, let's look at GPT, or the Globally Unique Identifier Partition Table style. Its partition capabilities include up to 128 primary partitions. There are no logical drives or extended partitions with GPT. GPT's maximum volume size is 2 exabytes. That's 2,097,152 terabytes. GPT does not utilize hidden sectors, but rather stores information in partitions. GPT does use replication and a cyclical redundancy check to provide for error correction. Now let's look at basic versus dynamic disks. You may structure physical disks in Windows in one of two ways, basic or dynamic drives. First, let's take a look at basic disks. Basic disks are considered simple volumes. The Windows operating system itself must be installed on a basic disk partition. If the operating system partition were converted from basic to dynamic, the system would become unbootable. In multi-boot configurations, only basic disks are compatible with other operating systems like Snow Leopard and Linux. Dynamic disks will not be available when booting into these operating systems. Basic partitions are limited by the same constraints as an NBR drive. Only 4 primary partitions total, or 3 primary partitions plus 1 extended partition, may exist simultaneously on a basic disk. Basic disks do not support mirroring, striping, or RAID. Now let's take a look at dynamic disks. Dynamic disks are organized into volumes, and the maximum number of these volumes is unlimited. Dynamic disks can create a single volume from the aggregate total storage capacity of multiple physical drives, otherwise known as spanning. Dynamic disks can implement spanning, striping, and RAID configurations with multiple physical disks. The 2 basic file systems supported in Windows are FAT32 and NTFS. Let's examine NTFS first, or the New Technology File System. It provides a permission system through the use of discretionary access control lists and access control entries. It provides for encryption and compression, which are both mutually exclusive. It provides a maximum partition size under NBR formatting of 2 terabytes, and a maximum partition size under dynamic or GPT formatting of 16 terabytes to 256 terabytes, depending on the size of the cluster that you use. It has a maximum file size of 16 terabytes. The other type of file system that Windows natively supports, FAT32 or File Allocation Table, provides for no permissions, no encryption, and no compression. It has a maximum partition size of 32 gigabytes, and this is only under the NBR basic partition style. It does not support GPT. It has a maximum file size of 4 gigabytes. In addition to FAT32, some older operating systems utilize FAT16. Again, this provides no permissions, no encryption, and no compression. Has a maximum partition size of 4 gigabytes, only under the NBR partition style, does not support GPT, and has a maximum file size of 4 gigabytes. In addition to all these aspects of partition styles and file systems, Windows 7 supports VHD files. VHD files are virtual hard drive files that can be used with products like VMware or Virtual PC Virtual Machines, or VMs, or created and managed with tools like Disk Management and diskpart.exe. These virtual hard drive files are drive image files that function as portable self-contained hard drives within Windows 7. The Windows 7 backup tool utilizes the VHD format when it creates an image of the current file system for backup purposes. Although these files are actual backups of Windows 7, they may also be mounted and manipulated by virtual machines. Windows 7 also includes a new feature called Native Boot. Utilizing the capability of Native Boot, the Windows 7 boot menu can be configured to boot directly from a VHD file without requiring a host operating system or virtualization application like VMware. This in effect gives Windows 7 users multi-boot capability without requiring multiple partitions for each operating system. Pretty cool, huh? Native boot entries are added to the boot menu with the command line tool bcdedit.exe. When these entries are selected, the user can natively boot into the chosen VHD file as though it were a separate partition and operating system.